Hi everyone, and welcome to our video on higher derivatives, concavity, and the second derivative test, where in this video we will be looking at just the higher derivatives. So higher derivatives or higher order derivatives can be useful to further analyze a function. For instance, the second derivative tells us how a rate of change is changing. So it's like the rate of change of a rate of change, which could help us answer questions such as if we have money in an account that is increasing, does that alone, that should be alone, does that alone make it a good investment? So it might just depend on how much it's increasing. So what it could tell you is maybe it's increasing a lot, but then it starts to just kind of go like that. And so maybe you don't really want money in that account anymore because it's not really going anywhere. Whereas something that might have started off slow starts to take off, and then you say, okay, this one looks a little better. So that's what it can kind of do. It tells you about how the curve is curving. So if it kind of just levels out, or if it's continuing to get steeper. So that's how we can analyze it. And then, well, we could always check with a calculator too if we have our function. All right, so the higher order derivatives. The derivative is a function, which means we can take the derivative of that to get a second derivative. And then we can keep taking the derivative and getting a third, fourth, etc. So our higher order derivatives have the form. So let's just start with our original function. So here's f of x equals y. And then our first derivative is the one that we've been doing. We usually don't say first derivative. We just say the derivative would be f prime of x. And the notation that we use if it's y is dy dx. Our second derivative, our second order derivative, is if we were to take the, let's go spell it. If we were to take the derivative of this, it would take a second prime. So f double prime. And then what it would look like over here is d2y dx2, like that. Okay, so just to rewrite it, so that's how it could look. Okay, anyway, so that's our other notation. So they just put little 2's on there. It doesn't mean square. That's why they offset them to remind us, hey, it's just the second derivative. The third derivative, well, the third derivative is if you put another prime on that, 1, 2, 3, and then x, and then, well, again, just change the number 2 into 3. So d3y dx3. And then the fourth derivative, let's go, I'll put it over here. Our fourth derivative, let's abbreviate it, derivative would be f. Now, they usually, so 3 primes is usually the max. Afterwards, they just put the number in parentheses like that. So they put the parentheses to mean that it's not a power. So without the parentheses, we would assume it's the fourth power. On this, it is telling us the fourth derivative. And then our notation there, again, would be d with a little 4 instead now. And then dx. They look like little powers, but that's that. Okay, and then it would continue the pattern. I'm going to do ... Often they'll say the nth derivative. So n is just some number you could put, like 5, 6, 7, 8, so forth. And so that means just change your number into that letter n like that for each of them. Okay, so that is our notation for the higher order derivatives. Now, the first and second are the most important. They have the most useful information. Afterwards, third, fourth, fifth, and so forth are usually kind of abstract ideas that are in math, but first and second have importance to them for applications. Okay, so before we do any applications, let's go ahead and do the derivatives of a couple of problems here. So in example 1, it wants us to find the second derivative, and then it wants us to evaluate. Okay, so let's go ahead and find this double prime. So let's do that first. Well, first thing you need is the first derivative. So let's go ahead and mark that as 1, just to say I'm doing 1 right here. So I really need the first derivative first. So f prime of x is needed. And then, well, this is just the power rule for the first term, so 12x cubed. Second term, also just the power rule, so plus 4x minus 9. And then that's it. So that's the derivative. And then the second derivative is now available to take. It's just take the derivative of this function. So power rule tells you 36x squared plus 4. And then derivative of minus 9 would be 0. That's it. Okay, so it's not anything special. It's just really 2 derivative problems in one. Okay, and then for the second portion, number 2 here, let's do f double prime of negative 2. Well, that is, evaluate this function just like we would any other function. It's just telling you put negative 2 into that. So we'd have 36, negative 2 getting squared, and then plus 4. All right, and then it's just order of operations. So f double prime of negative 2 is 36. Negative 2 squared is positive 4 plus 4. And then continue simplifying. 36 times 4 is 144. And then plus 4 makes that 148. And that's it. All right. So that gives us the number that they wanted. All right, which we can interpret eventually, but for now, let's just say that is just what they want. Okay, in example 2, it's saying find the second derivative. So this is just our different notation. And then this is how they might say to evaluate it. Okay, so it's pretty much the same 1 and 2 that we did from before, except this function's a little bit more complicated. Okay, so number 1, I still need the first derivative, so dy dx. This is using the product rule. Okay, so we have a product. There's our u, and there's our v. And so I have u prime v plus uv prime. And then with that, I can now substitute in. All right, the derivative of e to the x is e to the x. V is just the natural log of x, plus u, which is e to the x. V prime would be 1 over x. Okay, so there it is, and we could simplify. Dy dx is e to the x natural log of x plus e to the x over x. And then here's how we could continue with this and simplify and get the second derivative as is. But here's what I'm going to do first. I'm going to factor. Notice e to the x is in common in both terms, so that might make it a little easier. So dy dx is e to the x, and then ln of x, taking that out would be a 1 up top over x. Okay, so just a different scenario. Okay, so again, you didn't need to factor. This would require the product rule. This would require the quotient rule, though, so it's 2 different rules in one. Here, this is just the product rule, so that's why I wanted to do it. Okay, and then now that I have this, though, I can find the second derivative. So the second derivative, d2y dx2. Well, this is also the product rule. So I can see I've got, let's set it up, u prime v plus uv prime. Okay, so I've got my u would be this one. I'm going to use colors for this. And my v is that one. All right, so I ran out of room. Let's put it up here. So d2y dx2. All right, so u prime. Well, that's no big deal. E to the x has the derivative of e to the x. And then v is just that in the red, so the natural log of x plus 1 over x. And then we have plus u is e to the x. And then our v prime, so the derivative of this in the red, well, the derivative of the natural log is 1 over x. And then I see, well, this 1 over x is the same thing as, so I'm just going to just note it to the side. So note that those are equivalent. So instead of rewriting out the whole thing just for this, I know the derivative would be take the negative to the front and then minus 1 from the power to get negative 2. Okay, so there it is. And then even here, I can still factor this e to the x. So it's common in both. So this again is optional, but let's go ahead and do that. So I've got e to the x I'm taking out. And then I have the natural log of x plus 1 over x plus another 1 over x and then minus x to the negative 2. Okay, so it looks like I can simplify one last thing. I am going to do 2 things in one, actually. Let's combine these two in the highlighted yellow. And then let's go ahead and change that to a positive power. So finally, we have our second derivative is equal to e to the x times the natural log of x plus 1 over x plus 1 over x. That means there's 2 of them. So it's 2 over x. And then minus 1 over x squared. There we are. Okay, so that is our second derivative. So that took some space, but now let's take care of this evaluation. All right, so all that means, so d2y dx2, where x is equal to 1. So they're telling us plug 1 in to the x's that you see. So this is equal to e to the first natural log of 1 plus 2 over 1 minus 1 over 1 squared. And then we'll simplify. So this becomes, so e to the first is just going to be e. Natural log of 1 is 0. 2 over 1 is 2. 1 over 1 squared would be 1. And so this is e times 0 plus 2 minus 1 is 1. So e times 1, it all eventually simplifies to be just e. Okay, so that's how we can find our second order derivative with these problems and then evaluate it as needed. All right, so let's do one other in a different video. We'll put a pause, but that's it. So it's just do the derivative rule, do it again, just keep going. All right, so if you have questions, let me know. Otherwise, thanks for watching.